Hi everyone, welcome back to ChemHelp ASAP. In today's video, we are going to be talking about Gibbs free energy. Let's get started. Gibbs free energy is also known just as free energy. These are terms that we do use interchangeably. Gibbs free energy is a state function that is going to allow us to determine if a process is spontaneous, or what we also might say is if a process is thermodynamically favorable. So a system with a negative value of delta G is going to be spontaneous, or again, thermodynamically favorable. A system with a positive value of delta G is not going to be spontaneous or is not thermodynamically favorable. When using Gibbs free energy, we focus on the sign more than the magnitude. But let's talk about how we calculate Gibbs free energy. This is very similar to how we calculate enthalpy and also how we calculate entropy. We are going to take products minus reactants. So let's calculate the value of delta G for this reaction right here. Here is my table of Gibbs free energy. I just need to make sure that I plug these in the correct spot. My products are potassium chloride and oxygen, so just finding these in my table. Here we go right here. And Gibbs free energy, very much like enthalpy, if you have an element in its elemental state, like here we have oxygen as O2, its value for delta G will be 0. Those are my products. Now I need my reactant right here, finding it in my table. I'm plugging it in right here. Again, be very careful with your signs here. That is a common mistake I see, is signs get dropped or mixed up. Plugging all this into my calculator, I get a value of delta G of negative 236 kilojoules. So the question is this process spontaneous or is it thermodynamically favored? Well, our value for delta G is negative, so yes, this will be a spontaneous process. This is a thermodynamically favorable process. Now let's consider free energy and chemical reactions. One of the most important equations we use in thermodynamics is this one right here, because it's going to relate Gibbs free energy, enthalpy, and entropy. Let's calculate delta G for this reaction right here at 25 degrees Celsius. We are given a data table with our enthalpy and our entropy. First, I'm going to calculate enthalpy, or delta H. This is just products minus reactants. So here are all of my numbers plugged in, and I get a delta H of negative 198 kilojoules. I'm going to do the same thing for my entropy. Again, plugging all of my numbers in here, I get a delta S of negative 187 joules per mole. Now that I have enthalpy and I have entropy, I can plug into my main equation right here. Again, just plugging my numbers in. My 298K comes from my problem saying that this reaction was at 25 degrees Celsius. So just a quick conversion from Celsius to Kelvin. Now, before I actually put these numbers in my calculator, I need to make sure my units match. So my enthalpy, or my delta H, is given in kilojoules, and my entropy is just in joules here. These need to match before I can do any calculation. So I'm going to convert that joules into kilojoules. So now I have kilojoules per mole matching up with kilojoules here. I'm ready to actually plug into my calculator, and I get a delta G of negative 142 kilojoules. So is this process spontaneous at 25 degrees Celsius? Yes, because my delta G is negative. So it is also what we would call thermodynamically favorable. So how will temperature affect if something is thermodynamically favored or unfavored? Well, let's consider the same reaction, but this time instead of specifying a temperature, let's figure out what temperature this reaction will switch from spontaneous to non-spontaneous. Now, I've already calculated my enthalpy and my entropy for this reaction, so these numbers I just pulled from my previous slide. I am going back to my main equation here. But if we're switching between spontaneous and non-spontaneous, we are switching signs. which means we're going from a negative delta G to a positive delta G. That means delta G passes very briefly through 0, and that is when the switch happens. I'm going to set my delta G equals 0. That is going to simplify this equation to this equation right here. So plugging in for my enthalpy and my entropy, I'm going to solve for T, and I get T equals 1058 Kelvin. So now what does this mean? Well, it means when my temperature is above 1058 Kelvin, my entropy is going to control the spontaneity, or it's going to dominate the equation. Because my entropy is negative for this process, anytime entropy is going to dominate, the reaction is going to be non-spontaneous or not thermodynamically favored. And the opposite is true. So when my temperature is less than 1058 Kelvin, then my enthalpy term is going to control, or it's going to dominate my calculation. That means the reaction is going to be spontaneous, or again, thermodynamically favored, which is exactly what we saw on the previous slide at 25 degrees Celsius or 298 K. The reaction was spontaneous because we were less than this 1058 Kelvin, which is our turning point temperature. This calculation shows how temperature can influence if a reaction is spontaneous or not, but let's draw some more general conclusions about how the sign of enthalpy and entropy will affect if a reaction or a process is spontaneous. Using this equation, we're going to consider if enthalpy will dominate the delta G or if entropy will dominate the delta G. So we have 4 different scenarios. We can have a positive value of delta S and a negative value of delta H. When that is true, delta G will always be negative. So this is going to be spontaneous at all temperatures. Now let's consider the reverse. Delta S is negative and delta H is positive. Delta G will always be positive. So for that process, it's not going to be spontaneous at any temperature. The more difficult scenarios, I think, are when delta H and delta S are not in agreement in terms of the sign of delta G. So what happens when delta S is positive and delta H is positive? Well, then you have to consider temperatures. So at high temperatures, your T delta S term will dominate, which will give a negative value for delta G. That means the process is spontaneous. But at low temperatures, your enthalpy is going to dominate, and that is going to make delta G positive, which means it will be a non-spontaneous process. The reverse is going to be true if we have a negative value for delta S and a negative value for delta H. Again, at high temperatures, your delta S term will dominate. And when delta S is negative, at high temperatures, it's going to make delta G positive. So that will be a non-spontaneous process. But then at low temperatures, your delta H or your enthalpy will dominate, and that will make delta G negative, which will make it a spontaneous process. So when you have these last 2 situations, then you can do a calculation very similar to the one we did on the previous slide, where you can calculate the temperature at which the process switches between being spontaneous or non-spontaneous, or being favorable and non-favorable. The last thing I want to talk about is the correlation between Gibbs free energy and your equilibrium constant. So our equation that relates free energy and equilibrium is given right here. This R is the universal gas constant, but you will need to use the value of R that has units of joules per mole K. Your temperature does need to be in Kelvin, and you need to make sure that you are using the equilibrium constant and not a value that is Q. Let's do an example. The value of Kp for the synthesis of ammonia at 900 Kelvin is 3.7 times 10 to the negative 6. And the question is this reaction thermodynamically favored? So if it's thermodynamically favored, that means it is spontaneous. That means we should be getting a negative value for delta G. Let's see what we get. Using our equation here, I'm just going to plug in all of the values I know. Again, using this value for R, my temperature in Kelvin, and here is my Kp or my KEQ for my reaction. Let's do a little simplification first. So I'm going to multiply my R and my T, and I'm going to take the natural log of my K. Here we go right here. Multiplying these two together, I get a delta G of 9.35 times 10 to the 5th joules per mole. Usually we report this in kilojoules, so I'll go ahead and convert. So that gives me a delta G of 93.5 kilojoules per mole. But again, what are we really focused on here? We're not focused on the magnitude of delta G, but we're focused on the sign. Because if this process is thermodynamically favored, we should have a negative value for delta G. We do not have a negative value for delta G. We have a positive value for delta G. So no, this process is not favored at 900 Kelvin. Just like we could draw some conclusions about a spontaneous or non-spontaneous process based on our values for enthalpy and entropy, we can do the same thing between delta G and KEQ. So here is our generalization of our relationship between Gibbs free energy and our equilibrium constant. If delta G is 0, that means our KEQ is equal to 1. That's not usually the case. What is more helpful is to see that when delta G is less than 0 or it's negative, that is a spontaneous process, your KEQ is going to be greater than 1. And the opposite, of course, is also true. If delta G is positive, that is a non-spontaneous process, and your KEQ is going to be less than 1. So what was true about our example? Was our KEQ greater than 1 or less than 1? Well, our KEQ was definitely less than 1. It was 10 to the negative 6. So while, yes, I can calculate this out and actually get a number, again, we're looking at the signs. So now I can simply look at the KEQ and say this is less than 1, therefore my delta G will end up being positive, which means this reaction is not thermodynamically favored or it is non-spontaneous. I hope you found this video helpful, and thanks so much for watching.